In this part of my Arduino series, I'm going to take a step back and look at some of the electronics involved. Real basic stuff. Many of you will probably want to skip this because it'll be way below you. But for those who are approaching the Arduino with no electronics or little electronics background, stick around. This video will explain what a pull-up resistor is, what a pull-down resistor is, how you calculate resistor value for an LED, and even how to use a transistor to give you a stronger output on an Arduino, or to control a large relay, or how to hook a small relay directly to the Arduino. The most basic and the most useful thing to know is Ohm's law. They give school children this little memory device here. So you remember that E divided by either one gives you the other one. E divided by R gives you I, which is current. E divided by I gives you R. E is in volts, I is in amps, R is always in ohms. So E divided by R gives you current. I times R gives you voltage. The other thing I want to mention real briefly is we do everything in conventional current flow, positive to negative, as if power flew from the positive to the negative. This is called conventional current flow, and all semiconductors are going to be drawn in that way, anode to cathode in the current flow. The arrows always point in conventional current flow. In reality, we've known since the vacuum tube days that real current flow is that the actually going the other way around. The electrons, which are negative, are actually the ones that are flowing, and they're going the other way. They found that out when they had to heat, when they heated an anode and they couldn't get much flow to a cathode, but they just figured out when they heated the negative source, things worked a lot better. Anyways, we're going to go by conventional current flow, even knowing it's wrong, because that's what they do, and it doesn't really matter. So in this example, I've got a 6 volt power source, and it's going to, because the switch is closed, it's going to mirror itself across this 12 ohm load resistor, and so there could be 6 volts across the 12 ohm load or resistance. 12 down here, 6 up here, churns out 1/2. So my current flow is 1/2 amp. In a previous episode, I used a CDS cell. I used 2 CDS cells to make like the rudiments of a solar tracker, where it would read the 2 CDS cells and compare which one was brighter and control lights, you know, to indicate whether one was brighter than the other or whether they were even, more or less. I don't know what CDS cells for, like cadmium disulfide, I think, or something like that. It's basically a solar cell that doesn't make voltage, but it changes resistance instead of generating a voltage. So they look like this. They got a squiggly line in the center of them. And you can see it's in the sun. I'm getting about 400 ohms, dropping 5. If I cover it with my thumb, it goes higher. And I'm kind of deceiving myself here because I've got a, now with a flashlight on it, I can get it down a little lower. And I got some resistors hooked up and the other cell hooked in here, so I'm getting kind of a ghost reading here. It's got a wider range than that. But basically that's what happens. The bright light, the reading goes lower. Dim light, reading goes up. And so just out of guesstimation, I figured I'd use a 220 ohm resistor for a pull-down resistor on this CDS cell. Why did I need a pull-down resistor? Well, if I ignore the pull-down resistor and simply hook the CDS cell directly from the 5 volts through the CDS cell into my analog input on my MCU, which in this case is an Arduino, Well, the MCU or Arduino has got a real high input impedance. I wrote down 1 mega ohm. I don't really know. It might be 100K, it might be 50K. You know, it's something high though. Typically, it would be way up there, almost near like 1 meg. Your typical DVM is going to have a 1 meg input, more or less. This is a super cheap one, but a decent one will have a 1 meg input impedance. Well, this resistance is so high, and my range here, let's say the range of the CDS is 50 ohms to 1,500 ohms. 1,500 dark down to 50 ohms bright. I'm pulling those out of the air. It's kind of close to what it is, but I'm pulling those out of the air. Let's say that's what it is, though. Well, even at 1,500 ohms in the dark, contrasted against that 1 meg, that's nothing. It's barely going to influence that 5 volts at all. All that 5 volts is going to pretty much be seen here, because this isn't enough resistance to compare against this 1 meg. So in order to bring that into range, where I get a bigger sweep of voltages across that resistor, instead of virtually no sweep of voltages, I'd barely be able to see this difference from bright to dim if I had it set up like this. So it would be 5 volts to, 4.99 volts in my entire range. Again, I'm pulling that out of air. I could do the math for you, but I'd bore you to tears. So I use this pull-down resistor, in this case the 220 ohms. So this, when this is only 50 ohms, and this is 220, then I'm going to get almost, I'm going to get towards that 5 volts reading. If this is 1,500 ohms versus this pulling me down the ground at 220 ohms, I'm going to get a reading almost to 0. So this is going to be a good sweep of voltage between bright and dim for the CDS cell, and I'll see a big change of voltage on this pin. If I didn't have this pull-down resistor, like I said, all I would see is, from 4.9 to 5 volts, somewhere in that area. With this pull-down resistor, I get a much bigger swing in voltages. And I could have done the same thing in reverse. I could have put the CDS cell down here and a pull-up resistor up here. Just switch these two around. And I'd get the same swing of voltages, except I'd get them in inverse. I'd get the same amount of swing in voltages, is what I want to say. But they'd be inversely related. The high to low would be switched around. And then another note I put here is I drew a chassis ground here. You may see it more like this, which technically is an earth ground, but you'll see this symbol often for ground. Or on a little drawing for a lab drawing like this, you might just see a negative terminal, 0 volts I wrote down there. Which would be fine too. So any of those would work here. Just want to give you a little schematic change up over there. And I could do the math on this if you really want me to, and show you that the trickle amount of current, it's all going to fold across the big resistance. It's not going to be seen hardly by this little tiny resistance in series with it. For someone who really wants to see the details, if I didn't have this pull-down resistor, and it was just a CDS cell in series with the 1 meg ohm load of the MCU, again I'm guessing there, let's just use this, and this is the biggest number the CDS is ever going to be. This would be even a bigger example if I used the real small number the CDS can go down to, say 50 ohms here. But you can see even 1,500 ohms, which would be its max, versus the MCU, which is about 1 million ohms. You can see right there, without even doing the math, this is nothing compared to this. And if you put these two together and you put 5 volts across them, you add these two resistors together, you put 5 volts across them, you only get that much current. This would be in amps, or only 5 microamps. And so if you measure the resistance times the microamps, you can see the big load, which is the MCU in this case, the big resistance, is going to drop 4.9925 volts. That only leaves me 0.0075 volts to see my sensor. My sensor would only be that high at the most, and as this drops, it would be even less. So it's totally unworkable in terms of voltage sweep. I would only sweep, this little tiny fraction of voltage. So with the pull-down resistor hooked back up, the whole situation is much more manageable in terms of what I get in voltages. I've effectively given the microcontroller a 220 ohm input impedance, because I've gotten rid of that. That 1 meg input impedance is nothing compared to this 220, so just forget about it. Not even within the tolerance of the 220 ohm resistor. And you can see now I'm drawing 3 milliamps through this whole string here, not that unworkable 5 microamps, and I'm getting more realistic drops across the resistors. So the MCU is seeing this 0.64 volts right now, whereas the CDS is dropping 4.3 volts, but the CDS is at its highest resistance. It's only going to go down when it gets more light shining on it, all the way down to maybe 75 ohms or something like that. I'd have to measure it again. So you can see right now it's giving me a low voltage reading at the MCU, but as its resistance increases, it's going to take more and more of this voltage. If these were both at 220 ohms, if I had enough light shining in the CDS cell so that it was 220 ohms, then I'd get 2.5 on both of these numbers. I'd be seeing 2.5 on my MCU. So I'm starting at 0.64, I'm going up to 2.5, and as this goes even lower, I could even go higher than that. So I'm giving myself a good range of voltage to measure on my input of my Arduino. And I could play with that 220 ohm, and get it to match my CDSL even better. That's pretty good. If this microcontroller had a pin on it that I had defined as being high, then it would give me the voltage the microcontroller works at as a high. Usually that's going to be 5 volts. It can be 3.3 in some cases. Let's say it's a 5 volt microcontroller. I've got this pin turned on high, putting out +5. It's going to drive this LED and make it light up. If I have this pin undefined, or I make it low, low is just ground. So ground to ground, no current flow, it's going to be dark. So high, it'll turn on. Anything else, it's off. Now you can actually do the other way around too. You can actually hook an LED to positive and then make a pin go low. When the pin goes low, the LED will light in this case. It's acting like a ground for the LED. If the pin was undefined, it would be open, the LED would be off. If the pin was high, LED would be off. So you can see, this is normally what you'd be doing here though. You'd normally be driving it high to light up an LED. That's a simple case. Just to point out with the tri-state situation, you can actually do both. Actually turn an LED on by going low. Which in your circumstance, depending on what you're working on, you may need to do that. A tri-state buffer, or anything that works in a tri-state, isn't just on or off. It's actually got 3 states. When it's high, it's as if you're hooked to the +5. When you're low, it's as if you're hooked up to ground. When you're neither high nor low, when you're undefined, the pin's an open circuit. It's not connect to ground or to +5. So you've actually got 3 states. Plus, ground, open. I'm going to do a video showing how you can light 2 LEDs from 1 pin to illustrate this in more detail. But just for the sake of this video that we're on right now, let's just consider this. I'm going to be able to light this LED simply by driving this pin low. So not only can I light an LED by driving the pin high, I can drive the pin low and take power into that pin, lighting the LED. So I can light actually two LEDs from one pin. See, I've got the one pin being turned on, lighting a green LED. Then I turn the pin off, lighting the white LED, and then I give a pause when either one's lit. And I'll show you how to do it in a future video. Typical LED specifications. I'm going to give you some information on dealing with a typical LED. And I say typical in quotes. That's very important here. LEDs actually, there are some in the higher spectrum, UV and purple and blue LEDs, that can drop as much as 5 or 6 volts. That's not typical. Most of them are going to drop about 3.2 volts. There's also some real bright high power LEDs that can use way more than 20 milliamps max current. They got ones that can, draw several amps of current. These big high power units. But what's typical for your garden variety LED is 20 milliamps maximum current. You'll see that number all over the place. Very typical. And a very typical voltage drop is 3.2 volts. That'd be for like a blue, green, purple LED. A red LED may be as low as 2.2 volts. And yellow is going to be somewhere in between normally. It kind of goes up a spectrum, but you really have to look it up or test it yourself to really know. But 3.2 is a very typical, and 20 milliamps is a very typical numbers to use. So if I have a diode in series with a resistor, what a lot of people do, they just say, "Oh, I got 5 volts. I got a resistor. I want 20 milliamps. 5 volts divided by 20 milliamps. That's my resistor value," and it gives them a higher value. That's a safe way to go, but you're not going to get your maximum brightness out of your LED, and you actually don't want to push it all the way. If I was going with a blue LED at 3.2 volts, 20 milliamps, and I crank out the math here, well, I have to subtract this 3.2. So the resistor is only going to see 5 volts minus that 3.2 volts. And it's still going to see 20 milliamps. 20 milliamps to the resistor is the same as the 20 milliamps to this diode. The diode's not linear like a resistor, so Ohm's law doesn't really work on the diode. So you have to use it on the resistor. So I'm figuring out my resistor value to get 20 milliamps over the remainder of the voltage dropped across the resistor. That's going to come to 90 ohms, which is much smaller than you'll see a lot of people using. But if you really want full brightness out of your diode, out of your LED, that's what you would use. If it was going to drop 3.2 volts, which again is quite typical. Now, if it was a red LED, 2.2 volts, you'd turn that out, you'd get 140 ohms. In my examples that I've been showing you, I've been using 150 ohm resistors. So it's good to, not to put it right to the limit, unless you really know what you're doing, when you really need that last bit of brightness. Give yourself a little safety range. So 150 for all these, anything I'm going to do with the Arduino would be a good resistor for me to use. Give me a little safety, and it won't be quite pulling that 20 milliamps, but I won't be so dimmed out that I'm not getting the use of resistors. I see a lot of people just using a generic value. They'll use 220, or they'll use even 1 meg, 1K rather. And you'll see, if I used a 1K, it'll still light up. It'll still light pretty bright. It won't be as bright as it would be at 90 ohms, of course, by a good stretch. And in some of these cases, I'm flickering the LEDs. They're not really going to give me the full brightness anyways. That's why some of my LEDs in the last experiment I'm doing with the ping weren't all that bright. That's because they're only seeing a flicker. So in that case, it's kind of good to push them as hard as I can so I can see that flicker, all the brighter. I hope that makes sense to everybody. It's real simple math. The LED is going to tend to want to pull that voltage drop independent of current. It's going to vary a little bit with voltage, but it's going to really want to drop that 3.2 volts or whatever's typical for that LED over quite a range of current. So as the current increases, you'll drop a little more voltage, but not like a resistor. It won't really follow Ohm's law. The diode's going to have its own characteristic voltage drop that it wants to maintain. So you figure it out this way. Subtract the characteristic voltage drop from your total voltage and divide by the current you want for your LED. Voila. Simple, easy peasy. Well, I could talk all day about semiconductors, but for our purposes and to keep things very simple, I'm just going to go over diodes and transistors, bipolar transistors, in the simplest terms I can restrain myself to. I could go on and tell you actually how these devils work and everything else, but I don't want to glaze over too many eyes. Basically, a regular diode lets current flow one way and not the other. Positive to negative. The way the arrow is going in conventional current flow, a diode will let current flow that way. It won't let current flow the other way. So if I put a positive end of a battery to this end, and then a light bulb here, and then negative end of the battery, it'll light up. If I do it the other way, it won't light up. Now, the one caveat to that is, in the forward direction where it is letting current flow, it's actually restraining a little bit of voltage. Just like the LED had its characteristic voltage when in forward flow, it wanted to take that 2.2 or 3.2 volts out. A regular diode does the same thing, except that it's a lot lower voltage. And it depends on the type of diode you have. But for a typical silicon diode, which is mostly what you're going to see, in the forward direction, you're going to drop about 0.6 volts. 0.5, 0.6 volts, depending on how much current. It'll change a little bit with your current flow, but not a lot. A heavily rated diode, real heavy-duty diode, at its maximum current flow, getting the thing physically hot, maybe it'll drop a volt in the forward. And then maybe if you're talking microamps at a real low end, maybe 0.5. But really, that 0.6 is pretty typical. If I'm flowing an amp or two through here, I'm going to lose about 0.6 across. Cost of doing business. And usually there'll be little cylinders, like a resistor. You have a band on the one end that'll mark the cathode end. It's usually marked as a band. And it could be white with a dark band. Normally they'll be black with a silver band. LED, similar type thing, except your voltage, like I said, is much higher in the forward direction. The anode is normally made a little bit longer than the cathode. You can tell from the internal guts too if you know how to look for that. I'm not going into all that though. Just know that the anode is normally a little bit longer as a way to mark it. There's also a flat on the one side and all that. That's probably the most sure way to know the anode is longer lead. So an LED is a one-way device. A diode is a one-way device. In the forward direction, you'll drop a little voltage, and LED drops a little more, produces light. This just produces a little bit of heat where it's 0.6 that it notches out. Now, on the backwards flow, you've got a peak inverse voltage rating in a diode. Typical 4001 might be, I think, a 50 volt, and then 4002 I think is 100 volts, and then they go on by hundreds from there, or something like that. So you get as much reverse rating as you need. There's also something called a Zener diode, which is probably getting beyond our text now, but it's drawn like this. And that'll have a very specific reverse breakdown voltage, and they use those for regulating. But like I said, that's getting a little bit out there. And there's also something called a Schottky diode, which has a little less forward loss. And a little faster diode. Has some other characteristics too, though, that may be of interest or trouble to you. But basically that's a diode, a one-way valve. Move on to a transistor. A transistor can actually be drawn as two diodes. So if I was going with an ohm meter, looking at a diode, I'd put my leads across it. My positive lead here, my negative lead here. Some radio shack meters are actually got their ohm meter reversed. So you'd actually have to know that and mark your meter. That can really throw you off. But on most meters, the positive will be positive, because the resistance mode puts out a small battery voltage to test the diode with, or test the resistor with. So normally you'd put the positive lead there, negative lead there, you'd lose a certain amount. Normally in an analog meter you get about half current flow, about halfway, half reading. Many meters have a special diode mode, and they'll read like a half volt on a digital meter. You'll see that 0.5 I was telling you about when you're forward, and when you're negative it'll give you some kind of indicator. So that's simply testing a diode one way, then testing it the other way. You know it works, which way it works. A transistor can actually be tested the same way. For the example of an NPN transistor, which is the most common transistor around, they're a little cheaper and more readily available than a PNP or a FET. NPN's about as generic as they get. It can be tested with an ohm meter just like you were checking two diodes. From B to E you would check it like you've got one diode. From B to C you check it like you get another diode. From E to C you shouldn't get anything either way. So it would test just like this is drawn. Of course you can't make a transistor out of two diodes. In practice this is all one element, this middle element, instead of two, and it's made paper thin. And what that allows to happen is an avalanche to happen. So a little bit of current flowing through base to emitter allows for a lot of current from collector to emitter. And this is known as the gain, current gain, the beta, or the HFE of a transistor. Now a big old dumpy power transistor may have a beta as low as 20. But typically you'll see something more like, say, 100. So 10 milliamps going through here. Then I could flow 100 milliamps. I could flow a full amp going this way if the transistor was rated heavy enough. So a transistor with a heavy enough rating, I could switch an amp with only the 10 milliamps off the pin. And I can probably pull, these pins are made to pull, maybe in the 20 milliamp category for LED, not a whole lot more. I would do the resistor the same way in my last example. I'd take this 0.6 volts off of my 5. So I got 5 volts minus 0.6, so now I'm down to 4.4 volts. 4.4 volts divided by 20 milliamps, let's say, would give me that resistor. Well, here's a slight change. This is a pull-up resistor in this case. So let's say that this is high, this is flowing, then this resistor is going to be sunk pretty much to ground by this transistor. So I'll have a low coming out here. I have a high coming in, I'll have a low coming out. I take this high away, make this a low, the transistor is no longer flowing, then this pull-up will pull the voltage up to the supply voltage. So now I'm high. Now I've got a low in and a high out. So I've actually changed the phase. I've actually changed from a low to a high or a high to a low using this circuit. This would be could be called an inverter or a buffer, and it could give me a little more current flow if I needed it. Not much though, because I'm doing this resistor thing here where I'm folding the current across the resistor or not. And if I left this 200 ohm resistor in here and the same transistor, I have quite a leeway what I want to do with this resistor. It could be as low as, say, a 20 ohm resistor, which would be kind of foolish. It could be as low as a 2 ohm resistor actually on a 20 volt supply. No, it could be as low as a 2 ohm resistor. I'm trying to think of the extremes here. Let's say I had a 12 volt supply. This could be a 6 ohm resistor. I'd still have 2 amps flowing here. So that could be as low as a 6 ohm resistor for a 12 volt supply out here. You wouldn't do that, you know, unless you really needed to, for whatever you're hooking up to. Normally you'd want to make this as high as you can, take the burden off your transistor as much as you can, depending on what's needed over here. But now we're getting a little more esoteric and complicated, but I just wanted to go through a pull-up resistor and how it regards to a transistor circuit, because this is very common in audio, this type of stage. But we're looking more or less to turning things on and off at this point. We're not looking at audio. But this is very much how a simple audio stage might be set up, very commonly. Again, a pull-up resistor, and we're reversing the phase. We're going from a high to a low, or a low to a high. Here's an example with a PNP transistor. A PNP can also be drawn like 2 diodes, just the opposite way though. You can test it with an ohm meter just like you test 2 diodes that were wired this way. And again, a small current from base to emitter allows for a large current from collector to emitter. In this situation, I've hooked the emitter to the positive. I'd figure out my RB pretty much the same way, although I'd figure it out with this being at a low 0 here. So my plus whatever voltage to my 0 is how much current I want. Maybe I'd go for that 20 milliamps again with 5 volts. I'd have the 200 ohm resistor here again. But notice I need to be low here for this to work. So again, a low gets me a high, and a high here gets me nothing, gets me a low. But this would be giving me a higher current output and an inversion from my output pin. My pin would be inverted, high versus low would be inverted over here, but I'd have a lot more current capacity than I have here. So I could pull something like an incandescent light bulb, and then maybe that car headlight again like I was saying, or something like that. Incandescent light bulb. The other thing I could do, of course, would be to run a relay. Now, a small enough relay, they make small, very small relays called reed relays or dip relays that are about the size of a lot of them are the size of a dip container, and they have very low current capacity in the coils. And you can actually run the coils directly from an MCU to the coils. You may not even need snubber diodes because they're pretty much built into the MCU for something really tiny like that. Snubber diodes are a whole other ball of wax. Most people insist on them. So let's say here, I go to a coil. Then we go to ground, and this would control a relay switch, and this relay maybe can control 100 amps, you know, at 120 volts. You know, maybe I need to turn an appliance on or something. This coil would be too heavy duty for my Arduino, and a big relay like this would be too big for my Arduino to control directly. So I'd need a transistor to boost the current to it. And now what's normally done is they put what's called a snubber diode across this. This diode's in backwards deliberately. And what it does is when this transistor, say, abruptly stops letting current through, the current field will collapse around this coil and produce a back EMF, a reverse voltage across the circuit, which this diode will short out for you. This diode will return it for you and get rid of it. That protects the transistor. So there's 2 approaches here. You can use a transistor with plenty of voltage ratings and not even bother with this. Just what I tend to do. The normal good practice is to put a diode here. The thing about putting a diode here is you actually have to derate your terminal slightly. And I know some of you won't believe me, but look it up. So you actually don't get quite as hard of a slam on the contacts as you would as if this diode wasn't here. Kind of kill some of that energy, even if it's backwards energy from the collapsing field. So some say you need to derate your contacts slightly when you use a snubber diode, because you're getting a less robust slam on the contacts. Which again is the reason why I might just eliminate the thing and use a transistor with plenty of peak adverse voltage. You know, to withstand at least 7 times what the relay would be seeing. So if it was a 5-volt relay, maybe I'd be comfortable seeing a transistor with at least 35 volts, peak inverse ratings on it. But I'm getting into the nitty-gritty there. Normally you'll see that diode there. Here's a less kosher way of doing the same thing. Okay, this is an NPN again now, and I'm making the emitter current go through to turn the relay on. This isn't really the best practice because the emitter current is actually what's controlling this transistor. So any kind of funny back EMF off of this coil is going to affect this biasing current. That's why this really isn't the best way to do this. The advantages of doing it this way, though, is I would be in phase, and a high here would be a on relay. If I'm high here, a relay is going to be on. So I don't have that inversion I had with the last example, using the PNP and the emitter up here instead of down here. But again, your output should normally be off your collector, and your input signal should go through as less weirdness as it can. That's why the circuit fails. You're taking the output off the emitter, and you're also making the bias current see this funny load. So this is a less optimal way of doing things. And again, going back to the previous example with the NPN and the open collector, well, here's my collector all closed. This is probably the most sensible way to drive a relay. Easy peasy. I got my 200 ohm resistor, which could probably go up if this wasn't a super... I'm presuming this is a really heavy-duty relay. And I need quite a bit of current to pull it down. And I've got a pretty hefty transistor. Okay, so there's several ways you can go using transistors to amplify your current, to make your either invert your phase or don't invert your phase. This one I did invert the phase again, using an NPN transistor this time. So this NPN transistor is turned on, it's going to pull this pull-up resistor down to look more like ground, and there won't be enough voltage left over to run this relay. When this transistor is open, say this is a low, the transistor is off, then this resistor, this is basically disconnected now, and this resistor in series with this relay, we turn the relay on. So you'd have to choose a resistor that's small enough where it wouldn't interfere with the relay turning on. So maybe this would be something really low, maybe like a 20 ohm resistor. Maybe this is a 12 volt circuit out here. So what, 60 milliamps? Might be enough to turn on a fairly heavy relay. And again, you can have your snubber diode in there if you want. Well, that's a quick overview of some simple electronics, some simple electronic parts that you may be interfacing with your Arduino to do some real basic things. Now, the capacitor is the only thing I've really not gone over. And that could be a whole article in itself. If anybody really wants me to get into it, I will. Capacitors can be used for filtering, for bypassing signals, for filtering in terms of frequency, passing a certain frequency or not passing other frequencies. There's a lot to be said about capacitors. So I'll give you the nickel tour here. Current never flows through a capacitor directly. An electron on this side will never make it over to this side. I should have drawn that as a minus, actually. An electron will never cross this barrier. This is two plates separated by an insulator. But that doesn't mean that they're totally disconnected from each other, because when I pump a bunch of electrons on this plate, then a bunch of electrons are going to want to leave this plate, just because like charges repel. And then if I cut it out of the circuit, I've got a stored charge across this capacitor. But there's all kinds of neat things that you can do with a capacitor. A small capacitor will pass a high frequency signal right through, high frequency AC signal right through it, whereas a low frequency signal won't make it through it. So there's all kinds of things that you can do with a capacitor for filtering, for decoupling noise, for filtering frequencies. And in a way, a capacitor works opposite a coil does. So they actually do directly opposite things. A coil will pass low frequencies but block high frequencies. A capacitor in series will pass high frequencies but block low frequencies. And it's all relative to the value of the coil or the capacitor. And I'm not going to get too deep into all this resonant circuits and all that at this point. Just to let you know that there's a lot more to it. But for our purposes, just turning things on and off, sensing and controlling things, this is probably beyond the scope of what we need to get into. So maybe I'll do a whole video someday on capacitors. This isn't it. Comments and questions are welcome. I'm just learning this platform too, so there might be small mistakes, or I may not be able to answer every question, but I'll try. And I will be adding some annotations to these clips in future weeks here when I have time to correct a few gaps and other misspeaks. Thanks for watching.